Hello and welcome. Today we'll be looking at gas power cycles. And of course, we have five types of gas power cycle. First one there is the Carnot cycle. Have have the Carnot cycle, and the second one is we have the Octo cycle. Third one is we have the Diesel cycle. The fourth one is the dual cycle, and the fifth one is the Brighton cycle. All right. So these are the five types of gas power cycle. So we are going to be discussing one after the other. All right. So we are going to start with Carnot cycle. All right, Carnot cycle. All right. So under this Carnot cycle, we're looking at what Carnot cycle is. We'll be looking at the various processes in the Carnot cycle. We'll be looking at the P, V, and the TS diagram of the Carnot cycle. And of course, after that, we'll look at some notes on the diagram. After that, we'll look at the Carnot engine. And after that, we'll look at the delimitation of Carnot cycle. All right. So let's start. When we are asked what a Carnot cycle is, a Carnot cycle is a reversible cycle that gives maximum efficiency when compared to other cycles. All right, so let me write this. It is a reversible cycle. The definition of a Carnot cycle. All right, so said in this Carnot cycle, all the processes in this Carnot cycle they are reversible. So all the processes are reversible. So and we have four basic processes in a Carnot cycle. Four basic processes in a Carnot cycle. So let's write them from. We have from process one to two. From one to two. One to two is a reversible. It's a reversible adiabatic. Can also be called as isentropy. Bracket isentropy. Isentropy. Tropic. All right. So process two to three is nothing but reversible isothermal. Heat addition. All right. So process three to four, nothing but reversible adiabatic in brackets tropic. Tropic expansion. All right. So process four to one, we have a reversible isothermal. Heat heat. All right, so here are the four processes Carnot cycle. So we are going to explain this better at the time we draw the PV and TS diagram. So let's draw the PV and TS diagram. All right. So I will show you how to draw that when you watch. PV. So this is V. This is V. All right. So said process 1 to 2 is nothing but what? Reversible adiabatic compression. All right. So I'm going to have two states here. So let's one point here and another point here. So this I'm going to have a form. All right. We have two states. 1, 2. So we are going to trace it down to the side, and I'm going to trace this down as well. So this point, we are going to have here to be our V1, here is going to be our V2. And on this point, we trace it here. We're going to have here to be our P1 and here to be our P2. All right. So what do you notice? What do you notice here? It said reversible adiabatic compression means air. So we said the working medium in the gas power cycle is air, right? So now it means in this part from state 1 to 2, air has been compressed because you notice the volume has been decreased from V1 to V2, while the pressure has been increased from P1 to P2. So it means air has been what? Compressed. When air is compressed, pressure increases, while what? Volume increases. P1 to V2. All right. So now the next step is we have reversible isothermal heat addition. So here have another process here. All right. So here we have it for this. So here is going to be 2 to 3. All right. So for 2 to 3, we have reversible isothermal heat addition. Last one we are going to have like this. We are going to do another parallel line. All right. So from here, we are going to have another that is 3 to 4, and we are going to have 4 to 1. 4 to 1 will be like this. All right. So 4 to 1. All right. So now let's trace all these points down. We are going to have this to be our V4. If we trace this down, we're going to have this be our V3. All right. So let's trace this down out. Okay, before I trace this out, let me explain. All right, we said process 2 to 3 is reversible isothermal heat addition. It means from this state, from state 2 to 3, heat is being added after compression. All right. So for state 3 to 4, we said reversible adiabatic expansion. So after heat is being added, after heat has been added, the hair now expand. You can see from this point we are having 3 to 4. So if you look at this, we are having the volume increases from V3 to what? V4, while the pressure decreases from P2 down to what? To P4. So if we trace this point like this, so we are going to have P4 here, and we trace this out like this, I'm going to have this to be P3. So the pressure decreases from P3 to P4. So this is how we are to draw the PV diagram of a Carnot cycle. So let's put our arrow showing all these curves. So we are moving from 1 to 2. Then here we move from 2 to 3. Here we move from 3 to 4. And here we move from 4 to 1 in a cyclic manner. Cyclic. So believe you understand this. All right. So the next thing that we are going to be seeing here from this process 1 to 2, we said uh, we have compression. That is, work is being done on the what? On the gas. That is, work is being done inside the engine. So here we are going to have an arrow inside. All right. So here, let me clean this part. We are going to call here work done during compression process. All right. The next point from 2 to 3, we said we have heat addition, right? So we are going to add heat here. Let me add, let me put it somewhere here. So the arrow here is showing heat addition. All right. So for process 3 to 4, we said expansion. That is, uh, the air expand. After the addition of heat, it expand. This we have a reversible adiabatic expansion. So it expand. As it expand, we are going to as it expand, we have a work output. Is that clear? So when air expand, we have work output. So the arrow will be facing outside. This W, then we can say expansion. This work done doing expansion. So we have a work output. All right. So here, process 4 to 1, we have heat rejection. Heat is being rejected. All right. So here, and put some the arrow outside as well. It's going to be denoted by Q. So this is the diagram of Carnot cycle, that is the PV diagram. And of course, you know, for your thermodynamics processes, we are just having two processes here. We are having adiabatic, because two from 1 to 2 is adiabatic, from 3 to 4 is also adiabatic, and from 2 to 3 is isothermal, and from 4 to 1 2 is also isothermal. So, and during adiabatic process, we know that PV gamma is equals to what? Constant. All right, so let's just put that here. Let's showcase that here. We can have the arrow pointing outside like this. Also have another arrow here in this side of this curve like this. Then we are going to say PV gamma equals to constant. All right. So this is a complete diagram of the PV diagram of a Carnot cycle. All right. So now let's look at the TS diagram. So let's write here PV. Let me just write it here. PV diagram. Is a PV diagram. All right, so now the next thing we'll be looking at is the TS diagram. All right, so let's go for the TS diagram now. Watch carefully as I draw this as well. I'll explain it to you. Right? So now, this is our T, that is temperature entropy diagram. All right, so now, here from process 1 to 2, we are having a curve. So every curve on our PV diagram will be a straight line on our TS diagram. So now let's start. I'm going to have a straight line here. All right, so this process is going to move from 1 to 2. All right, and we trace it down. What do you observe? We are having a straight line, right? So it means we are having a constant entropy here. That is, our x1 will be equals to s2. So here x1 is equals to s2. All right, so for process 2 to 3 now, 2 to 3 is also a curve, so it's going to be a straight line. All right, so this is 3, going to be a straight line. So now you can see it's a straight line, so we are having a constant what? We are having a constant temperature here. We trace this point, so we are tracing this down. So from process 3 to 4 is also a curve, so it's going to be a straight line as well. It's going to be a straight line. All right. So for process 4 to 1 is a curve, so it's also going to be a straight line. All right. So we can say this is 4. So by the time we trace this down to, we are going to have our x3 to be equals to x4. x3 to be equals to s4. And here we are going to have T1. T1 will be equals to T4 because we are having a straight line. So T1, let me clean this part. Okay, let's call this place T1. Let's call this place T2. But we are going to note that T2, I'm going to note that T2 is equals to T3 and T1 is equals to what? T4. All right. So this is the TS diagram of a Carnot cycle. All right. Now, we said, what other point do we need here? All right. We said that process 1 to 2 is a reversible adiabatic compression. But on the TS diagram, and during that process, I explained to us that the volume of air reduces from V1 to V2, while pressure increases from P1 to P2. But if you look at our TS diagram now, during compression process, we have our temperature. The temperature increases from T1 to T2. Is that clear? All right. And so we can conclude that during compression process, the volume of air reduces while the pressure and the temperature of air increases. Is that clear? All right. So now again, we said from 2 to 3, we have reversible isothermal heat addition. Reversible isothermal heat addition for 2 to 3, but on the TS diagram, that happens at a constant what? Happen at a constant temperature. Is that clear? That is T2 is equals to what? T3. So for us to have heat addition on the Carnot cycle, it must have occur at a what? Constant temperature. All right. So now for 3 to 4, which is called reversible adiabatic expansion. Reversible adiabatic expansion from 3 to 4. The TS diagram is 3 to 4. So that happens at a what? At a constant isentropic process. That is S3 is equal to what? S4. All right. And again, the lastly, we have 4 to 1. This 4 to 1 4 to 1, which is a reversible isothermal heat rejection. So on our TS diagram, we have that to happen at a constant temperature. Exactly. So here we have a constant temperature. For heat addition, it must occur at a constant temperature on the TS diagram. For heat rejection, it must occur at a constant temperature as well. All right. So for process 1 to 2, it must occur at a what? At a constant entropy. And for process 3 to 4, it must occur at a constant entropy as well. I hope you get this correctly. All right. Now, the next thing here is let's put our work input. So we said work is done in the engine. So we have arrow here going inside. So we are going to have work done in the end, that is work done during the compression process. And we said heat is added, this QA. And here we have work output. That is after it has been added, the hair expand. That is thereby producing work output. So we are going to have W is work done during expansion. And here we are going to have it being rejected. That is QR. All right, so this is the PV diagram, while this one is the TS diagram. All right, so done with the PV and the TS diagram. So the next thing is we are going to note some things carefully here. I'm going to clean this part, then we are going to still write some notes on the PV and the TS diagram. So the next thing is we want to write some notes on this. All right, let's start with from process 1 to 2. What can we note from process 1 to 2? So we said the process 1 to 2 is a compression process. So let's write some things here. So during compression process, during compression process, all right, during compression process, what do we have? Let's take a look at this. Said air is compressed, right? Air is compressed. That air is compressed. Air is compressed. That air is compressed. And what happened here? We see that the temperature and we see that the pressure and the temperature increases, right? So we said during compression process, air is compressed by increasing. Air is compressed by increasing its pressure and temperature. By reducing its volume. By reducing its volume. So I believe this point is clear. Because here, when during the compression process, you observe that pressure increases, and on the PV diagram and on the TS diagram, temperature increases, but the volume reduces. Is that clear? All right. So after the compression process, after the compression process, after the compression process, all right, after the compression process, heat addition takes place, right? So heat addition takes place. Heat addition takes place, and the process is what? And the process is a reversible isothermal process. And the process and the process is isothermal. So now, after the heat addition process, after heat addition process, after the heat addition process, what do we have? You see that air expands, right? See that the air expands. Air expands. How? Isentropically. I've explained that before. Isentropically. Isentropically. So see that after the heat addition process, air expands how? Isentropically. Thereby producing what? Producing work output. Thereby producing work output. All right. So now after that, after the expansion process, what do we have? So let me write after the expansion process, after the process. All right. After the expansion process, the air should reject heat. The air, the air should reject heat from the engine. From the engine. The air should reject heat from the engine. From the engine. How? This is going to do that at a what? At a constant. That is at sorry. It's going to do that at and the process is going to be what? An isothermal process. The process, or let's write at a constant temperature. Because if you go to the TS diagram from 4 to 1, you have 4 to 1, which is this 4 to 1 is a constant temperature. So let's write after the expansion process, the air should reject heat from the engine at at a constant temperature. All right. So these are all the points you need to note. So we are going to explain this. We are going to explain this further using a Carnot engine. So let me clean this part. So we look at a Carnot engine. Let's look at the diagram of a Carnot engine. All right. Let's look at the diagram of a Carnot engine. Okay. I have the cylinder head. All right. So this is the cylinder head. We are going to have the cylinder wall. Cylinder wall. This is another wall here. All right. Let's shade this. All right. All right. So here is the cylinder wall. Now the cylinder wall. All right. So here is the cylinder head. All right. So here is the cylinder head. All right. So for a for when you consider this Carnot engine, for a Carnot cycle, this cylinder wall is a perfect insulator. So it's a perfect insulator. All right. Why this one is a perfect conductor? It's a perfect conductor. All right. Now, if we have air inside this Carnot engine, let's assume we have air inside this Carnot engine. We have air here. We have air inside of this part now, and we have a piston. We have a piston here. All right. All right. So we have a piston inside this engine that is compressing the air. Is that clear? All right. So if the piston compresses the air, because we are saying from process 1 to 2, we have compression, right? All right. So if the air is compressed by this piston, all right. So the air is compressed by this piston, right? So now we are going to, because this cylinder head is a perfect conductor, so we are going to we now bring a heat sink. We are going to bring a heat sink closer to this cylinder head. So we are going to have a heat sink, something like this. So heat sink. So which, when it is brought to that, it is at a high temperature. So it's going to be brought closer to this cylinder head. So it's going to transfer heat. Inside this engine. So as the air inside the Carnot engine receive heat, is going to expand, thereby pushing this piston backward, right? So after the expansion process has complete, we are going to need to remove the heat inside this engine, because don't forget this heat sink is at a high temperature, because it's going to transfer heat inside this air. The air is going to receive heat, then it's going to expand. Exactly. So when it expands, it's going to push this piston backward. So after the process has been complete, the heat still remains inside the engine. Now we want to remove the engine. So for us to remove the heat inside the engine, we are going to need a, oh sorry, this is going to be a heat source. Sorry, heat source. Sorry, we are going to need a heat source at a high temperature. So now for us to remove the heat inside this Carnot engine, we are going to need a heat sink now, because when we say sink, the heat sink is a reservoir where heat emission is being dumped. All right. So now we are going to have a, let's put our heat sink here. Sorry for that. All right. So we are going to have a heat sink here. Going to have a heat sink. All right. So now, and mind you, this heat sink is at a low temperature, and you know heat flow from a high temperature to a low temperature. Is that clear? So now, the heat inside this Carnot engine now will move to the heat sink. This is going to move to the heat sink. So this is the explanation, and this is the explanation to this. And you are going to note, because the cylinder wall, is a perfect insulator. That is perfectly insulated. So the heat transfer there is going to be equals to 0. Please take note of that. Because the cylinder wall is perfectly insulated, heat transfer, here, the heat transfer will be equals to 0. And don't forget, we can also denote this as Q is equals to what? 0. All right. So these are what you should take note here. So don't forget, this is the diagram of a Carnot engine. Let's write it somewhere here. This is the Carnot engine. All right. So now I think this point now is clear to you. So said after the expansion process, the air should reject heat from the engine at a constant temperature. So I've just used this Carnot engine to explain that point. And for the case of exam purpose, take note of this, because the cylinder wall is perfectly insulated. So the heat transfer in this Carnot engine equals to what? 0. So the next thing we are going to be looking at after this is we are going to be looking at the limitation of a Carnot engine. So let me clean this side. At limitation, please, I almost forget this. So let me quickly write the efficiency of a Carnot cycle here. So let's look at efficiency here. All right. So the efficiency of a Carnot cycle is denoted like this. All right. The efficiency of the Carnot cycle is going to be that is T maximum, that is maximum temperature minus minimum temperature all over maximum temperature. So, and our maximum temperature is the temperature we are getting from the heat source. So this can also be written as heat source minus what? Heat sink all over what? Heat source. All right, so this is how we are going to denote our what? Efficiency of a Carnot cycle. All right, take note of that. So let's look at limitation now. The first limitation of a Carnot cycle is it is not restricted by the kind of fuel. All right, it is not restricted. All right, so it is not restricted by the kind of fuel. This it can be used anywhere. All right. So now the next one is number two. During we have two processes here. We have the adiabatic process and the isothermal process. So during the adiabatic process, the piston should be made to move, at least should be made to move at a very high speed, so that the working medium, that is the air, cannot exchange it quickly. All right, so let me write that point here. During adiabatic process, the piston should move at a high speed so that air not exchange heat, not exchange heat in heat quickly. All right. So we said, during our adiabatic process, we have two processes. We have the expansion and the what? And the compression. We have the compression at this side. We have the expansion at that side. So during the adiabatic process, uh, either compression or expansion, piston to be made to move at a high speed so that the working medium, which is the air, cannot exchange it quickly. All right. So now the next one, the third, the third one is doing isothermal process. We have isothermal process for the heat addition, and we also have isothermal process for the heat rejection. So during this process, the piston should be made to move as slow as possible so that temperature cannot change quickly. All right, so let's write that. During doing isothermal process, during isothermal process, the uh, piston piston should move low speed so that temperature 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 will not, let me read, will not change quickly. All right. Now, this is the third thing. So the fourth one is now, is it possible for us now to have an engine now that is going to that the piston will increase, that the piston will suddenly increase during adiabatic process, that is doing the doing that is doing the so it is not possible for us to have an engine that is going that the piston will suddenly increase in speed and the piston will also reduce in speed. That clear? You cannot have an engine operating that the piston will increase during adiabatic process and the piston will also reduce during isothermal process. So let me write the fourth point here. So now we are on this point 4, said it is not possible to have an engine which the piston will suddenly increases during adiabatic process and suddenly reduce during isothermal process. So due to the following reasons above, due to this from 1 to 4 above, Carnot cycle is not a practical cycle. So it's just a theoretical cycle that is used to that is used to compare the efficiency of other cycles. So and there is no cycle that can have that the efficiency can be more than the Carnot cycle. So the Carnot cycle is cycle that gives the maximum efficiency. So other cycle are used to other cycle efficiency is used to compare with Carnot cycle. They cannot actually be equals to or greater than the efficiency of the Carnot cycle. So this is just the introduction to Carnot cycle. So stay tuned for examples, these calculations and calculations. Of course, you know us, we are going to give it to you. All right. So thank you and stay tuned.